When the AI industry talks about safety, they almost exclusively mean behavioral alignment. Techniques like RLHF, RLAIF, and constitutional AI are built on the assumption that a probabilistic system can be trained to be intrinsically safe. These techniques attempt to force a model to reliably refuse unsafe behaviors. They do this by mathematically shaping its loss surface during training, effectively building a statistical barrier against generating harmful outputs. The mathematical flaw in this approach is that the space of possible user inputs is functionally infinite. The gradient used to shape that loss surface is simply too imprecise to guarantee refusal across all edge cases. Once a model is deployed, the surface area it faces will always exceed its original training distribution. It encounters inputs and environments that the loss surface was never designed to handle. Because failure modes naturally exist where the weights fail to catch them, treating a probabilistic system as definitively safe from inside its own weights is structurally impossible. This theoretical brittleness is backed by a 5-year empirical track record. Alignment interventions routinely fail under modest adversarial pressure. This chart visualizes the failure rates of 25 different frontier models against simple adversarial tactics. When researchers prompt these models using adversarial poetry, literally just writing a harmful request in verse, the model's refusal mechanism is bypassed 62% of the time. If you wrap that same harmful content in a basic JSON structure, a tactic known as a format lock attack, you bypass current frontier systems 30 to 42% of the time. Place those models in a multi-agent context, and the safety alignment breaks at a rate of 46%, with a median time to failure of just 16 minutes. Bypasses like these emerge directly from the nature of generative probability, rather than isolated, patchable software bugs. Betting on the next iteration of behavioral training as a load-bearing fix is a doomed bet. To guarantee safety, the trust boundary must be moved completely outside the model. The alternative is architectural safety. This approach relies on deterministic code, strict isolation boundaries, and policy gates that entirely surround the model. In an architectural system, the model's own refusal is strictly a best effort layer. The deployment architecture surrounding it is authoritative. To see how this works in practice, look at embodied AI, specifically vision-language-action models driving humanoid robotics. Embodied AI operates in a kinetic action space. It can take physical actions that are impossible to fully anticipate or restrict using training data alone. The architectural solution here is a cognitive cage, a deterministic safety hypervisor that wraps the neural network. This hypervisor intercepts every single motor command the model proposes, verifying it against hard, deterministic physical limits, like maximum force and velocity. If the model hallucinates an unsafe action, the deterministic layer simply rejects the command before the actuator ever fires. Affordance hallucinations in robotics do not result in kinetic trauma when the action space is constrained by unyielding code, rather than the model's own sense of caution. This exact same principle applies to cognitive and emotional deployment services, such as therapeutic AI. Relying on a probabilistic model to accurately self-identify when a user's input escalates into a genuine human crisis is a high-stakes vulnerability. The architectural fix involves 3 layers, starting with pre-model input classification. Deterministic classifiers analyze the incoming message for crisis signals. If triggered, the system routes the user to a human protocol and completely hides the prompt from the model. For normal inputs that do reach the model, the architecture applies a constrained output surface. It prevents the model from generating free text responses. The model is forced to emit data into structured schema fields. This allows deterministic validators to analyze, rewrite, or refuse any outputs that violate policy. The decision to escalate a crisis to a human must be externalized to the architecture. The model is completely removed from making high-stakes emotional judgment calls. The challenge compounds in multi-agent systems, where independent models communicate directly with one another. Single-agent safety alignments break down here because agents constantly generate inputs that neither model was explicitly trained to handle. The architectural solution is a semantic firewall, a trust boundary enforcement layer that sits at the protocol level between agents. This firewall assumes every inter-agent message is untrusted by default. explicitly classifying and sanitizing payloads before any reasoning is allowed to occur. The architecture explicitly gates information sharing. No agent implicitly inherits the potentially toxic context window of another. When AI systems talk to each other, you cannot rely on making each individual agent safer. True safety must live in the mediated, heavily guarded protocol between them. Every safety architecture shares 5 moves. 1. Wrap the model in deterministic code. 2. Explicitly bound its action surface. 3. Assume adversarial inputs. 4. Gate failure modes at runtime. 5. The trust boundary lives in the architecture, reducing the model to an overridable component. Any system missing 2 or more pillars relies on training time hope rather than a rigorous safety architecture. When you apply these pillars to the current industry, the gap becomes clear. Most press releases announcing new AI safety techniques describe behavioral training, not safety architecture. Deploying model cards, evaluation reports, and capability tests without hard runtime limits is compliance theater. It means an organization has done the model work, but not the safety work. Giving any behaviorally aligned model direct, unmediated access to an action space is categorically dangerous, regardless of its benchmark scores. This distinction matters for regulation. Mandating a safe model is legally unenforceable because you cannot audit a probabilistic system into compliance. Policymakers must focus on regulating the deployment architecture. Mandating runtime layers with specific properties moves AI policy from mathematically impossible to practically enforceable. Moving from behavioral to architectural safety shifts the heavy cost away from the training cluster and onto the runtime deployment, requiring scarce engineering talent. While this runtime architecture is complex and imperfect, the cost is honest, it is transparent, and it is verifiable in the deployed code. Behavioral alignment will never mathematically catch the infinite edge cases of reality. Safety must be built into the deterministic systems surrounding the model, or it does not exist anywhere at all.